Good day, my name is Manuel Ferrer and I'm here to discuss with you the hidden topologies when polychromatic structural light is tightly focused. This presentation is based on our recent work Polychromatic Electric Field Notes, which is currently submitted to peer review, but you can find the preprint on the archive. This is the outline of our talk. First, I will provide a brief summary of the curves traced by the electric field as it evolves in time. Then I'm going to present some basic concepts from knot theory that are relevant to our work. Later on, we will discuss how we can create knotted polarizations using non-paraxial light, and finally, I will show the most important results of our work. It is well known that the tip of the electric field traces complicated curves as it evolves in time. For the monochromatic case, these curves reduce to the polarization ellipse. In the past decade, researchers introduced dichromatic polarization states generated by collinear superposition of two beams, leading to quartic plane curves, also known as Lissajous-like figures. In 3 dimensions, a monochromatic electric field traces an ellipse that no longer lives on a plane that is orthogonal to the propagation direction. But what about the polychromatic case? Since now each harmonic component can oscillate in different directions, the polarization curve can become non-planar. This new zoo of possible polarization states has been almost been unexplored, so it raises the question, is it possible that the electric field forms knotted trajectories? In order to solve this question, first let me define what I mean by a knot. For us, a knotted curve is a closed curve with some given periodicity, is embedded in 3D, and the curves do not self-intersect. Under this definition, this is a knot. In fact, it is a trivial knot, known as the unknot. However, we are interested in the cases that the curve has multiple crossings and it cannot be deformed into another kind of knot without self-intersecting. To differentiate one from another, mathematicians have defined invariants, which are functions of a set of knots that do not change unless the knot changes. In other words, it has the same value for all the equivalent knots. In order to create a connection with the polarization curves, let me start by defining a closed parametric curve C, where x, y, and z are smooth functions of time. Then, we can approximate these functions using a truncated Fourier series. The resultant structure is known as the Fourier I-J-K knot, where the indexes indicate the number of harmonic components in each oscillation direction. One important property is that, since it is always possible to approximate any harmonic function using the Fourier series, all knots are Fourier knots. In fact, we can focus our attention in the case when I, j, and k are equal to 1, also known as the Lissajous knots. It must be noticed that in this case, the frequencies of each component are proportional to coprime numbers. In fact, last year, the first work on how to create knotted polarization curves was presented. These curves can be generated by interfering 3 monochromatic plane waves propagating along with orthogonal directions, carrying different frequencies and polarizations. However, the implementation and measurement of these polarization states are extremely complicated. In contrast, we propose a different way to obtain knotted polarization curves using tightly focused structural light. It is well known that when optical beams undergo focusing by means of a high numerical aperture lens, a non-negligible longitudinal component arises, leading to the generation of complex and exotic 3-dimensional polarization topologies. In this case, the time-dependent fields at a plane in the focal volume are obtained by numerically calculating the Richards-Wolff diffraction integral. It is noteworthy that the spatial extension of a tight focused beam decreases with the frequency as it can be shown in the figure. At first try, one could start by considering the simplest possible case: 3 Gaussian beams with different polarization states and frequencies. Here, we show 2 possible configurations of the structure field already discussed. A red marker indicates the existence of a knotted polarization curve. Notice that knotted polarization states are present in both cases, but the populations of these exotic states are relatively small and only contain threefold topologies. In order to develop a strategy to obtain a larger population of knots, Let's pay attention to the action of a lens on the polarization state of the input beam. To calculate the focus field, we can decompose the incident field into radial and azimuthal components. By following the ray through the lens and to the focal point, it becomes evident that the radial component generates a larger longitudinal component due to the induced tilting of the wavefront. Meanwhile, the azimuthal component remains almost unchanged. It is noteworthy that a plethora of complicated polarization curves is expected due to the non-uniform amplitude distribution arising from the type focusing. Following these insights, it is worthy to consider the three-dimensional polarization pattern obtained from tightly focused vector vortex beams. In particular, we'll be using the family of cylindrical vector beams, which are characterized by a topological charge L and a relative phase delta between the circularly polarized components. As shown in the panel A of the figure, we obtain a large longitudinal component since the beam is radially polarized. In addition, pay attention to the cases in which L is set to -1. Notice that the polarization pattern is the same except for a rotation, making the major axis of the ellipse to be coplanar and pointing to orthogonal directions on a plane in the focal volume. Therefore, it's a little bit intuitive to say that a Taylor superposition of radially polarized beam and these other cylindrical vector beams allow us to create the three oscillation planes that we need to generate knots. After this, we reconstruct some polarization states and we get, as you can see from the figure, we succeed in obtaining a spatially varying distribution of complicated polarization curves. Despite the beautiful and impressive figure, we still don't know if we have created knotted curves using this heuristic method. So take one of these curves and ask yourself, is it a knot or not? Therefore, we still need to identify and classify the different types of knots. Once some knots are easily recognizable, we decided to use numerical tools to perform the identification and classification. In particular, we used the Python package PyKnotID, developed by the researchers of the University of Bristol. The identification protocol can be resumed as follows. First, we select one position on the focal plane and reconstruct the polarization curve. Then, we proceed to identify the type of knot using some knot invariants, such as the knot determinant and the Alexander polynomial. We also test the chirality of the knot by calculating the Jones polynomial. Then, a pin is placed to localize the knot onto the focal plane. We continue repeating this protocol for a large number of sample knots, so it is possible to identify regions where the knotted curves exist. Here, we show some results for the cases in which the frequencies are related to each other by the first two sets of coprime numbers. The results in the first column are the case when the frequencies are proportional to 1, 3, and 2 respectively, while in the right column is the case when the frequencies are proportional to 2, 3, and 5. The first column shows the amplitude profile of the tightly focused beam overlaid with the curves traced by the resulting knotted polarization vectors. The second row shows the regions in which the different knotted structures are located on the focal plane, while the histograms show the relative probability density of the different knot topologies within the considered region. As you can see, both cases present a large population of knotted curves very well localized. In particular, for the 10,000 analyzed curves, almost 11% are identified as knots for the first set. However, only 3 topologies are generated: on knots, trefoils, and figure 8 knots. Meanwhile, almost 25% of the analyzed curves were not trivial knots for the second case, and the existence of more topologies proved to have a richer but more complicated polarization distribution in the plane. As it was mentioned before, the necessary non-negligible longitudinal component arises only when focusing a radially polarized beam, while the remaining terms generate transverse bases on the focal volume. Therefore, One may ask how the distribution of noted polarization states varies when the relative amplitude of the longitudinal component changes. Here, we show the spatial distribution of the polarization curve at the focal plane by type focusing the previous introduced vector beam when the frequencies follow the relationship 1, 3, 2. Notice that for all the cases, only 3 false and figure 8 knot polarizations are created, indicated by red and yellow markers respectively. These results provide us with a tool for tailoring the polarization distribution and relative size of the population of the knotted trajectories. Heretofore, we have considered the existence of knotted polarization states exclusively on the focal plane c equals to 0. A more complete analysis should include the evolution of the three-dimensional polarization distribution upon propagation in the focal volume. As shown in the figure, knotted structures adiabatically follow the beam propagation. In fact, trefoil knots are present in a region that extends beyond the fundamental wavelength lambda for the first case, but they start to disappear because the longitudinal component becomes negligible again, far away from the focus. In conclusion, we have introduced a heuristic criterion to generate large and rich population of locally knotted polarization curves by tight focusing three structure beams at different frequencies. These structures can be generated and detected with the current techniques developed for nonlinear optics and nanophotonics. Regarding the application of these exotic polarization states, we foresee their relevance in the field of light-matter interactions when they might induce local three-dimensional magnetic phenomena in semiconductors. Before finishing my presentation, I would like to thank Professor Ibrahim Karimi and the members of the SQ group for their support, especially to my co-authors Alicia Sid and Alessio De Rico, and our collaborator in MIT, Hugo Larocque. Thank you for your attention.